2. That seems to work okay. Oops, my little thing's closed. There I am. Good morning, folks. How's everybody going? Start my recording. Close that guy. Alrighty, just getting my windows ready. Wow. Ah. So, welcome to the lecture for this week, week 10. Things are getting pretty serious now, aren't they? We're now closing in rapidly on the end of the semester, which is really a nice place to be. After a while, it's always, I suppose you might feel it's very stressful. You've got assignments and the looming threat of exams coming up, but also we're sort of coming to the end of our journey through all of these topics. So I hope that you feel like you have a lot of knowledge that you're sitting on right now, and that a lot of skills which you've been developing this semester. And really, although I see it as you have a job to do in terms of being on top of this big pile of knowledge that you build in each of your courses, and building your skills a little bit more, in a certain sense, you've already done a lot of the hard work, which is to get from 0 to something. And particularly in this course, I was thinking a lot about the assignments. The second assignment was handed in on Friday, and third assignment has just been released. And I was thinking back on the first assignment and thinking how hard the first assignment is compared to the second and third assignments. That's not to say that the second and third assignments aren't complex. They're certainly more complex than the first one. But when you do the first assignment in this course, in that week when it's released, you only have a very beginner's knowledge about how to do anything in assembly programming. The assignment gets released in the same week where you learn what a label is and where you learn how to do conditional branching. And now we're way past that, looking at much deeper topics. So your ability to write some code that does something in assembly programs is now much, much higher. And I think that everybody is finding that even though the assignments are more complex, your skills are much, much higher. So they might be a little bit more approachable. And similarly with all of the topics in this course. In fact, there's a lot of topics which we're now looking at, networks, operating systems, architectures, which you have this foundation for in terms of understanding how computers really work, understanding what instructions are, understanding about assembly programming, understanding about the hardware-software interface. And even though we now have to add this kind of broad base of knowledge about these big phenomenon networks is one, operating systems is another, how CPUs are designed is a third one. You can ground that knowledge in your understanding of the fundamentals now, which I think is really, really valuable. So I might just make myself online over here rather than do not disturb. Over here I've got my VS Code Codium window. I upgraded to Ubuntu 20.04 on Saturday. Fun times. My computer then wouldn't log in, or at least I couldn't log in with my user account on Ubuntu because I had fractional scaling set up on my screen. Of course, I could log in with the terminal, but not the desktop. So I got that fixed up, made sure I could stream. Then I thought, oh, I might do a demo in VS Codium today or Friday. And then I find that it wasn't working and it needs to sit there and spin and install Platform Yo again and everything. So I'll just forget about that today. We'll just we'll just talk about topics today, I think. Now, a little bit of news. I've already mentioned this, but I hope you don't mind if I'm just taking it slowly in the first 10 minutes of the lecture. Not lecture/deliverables. I know there's a few people who roll in a little bit late. And it's nice to just make sure that everyone's on the same page. Synth, big tick, done. Sequencer, big tick, done. Now we're up to networked instrument. This assignment has now been released. I'm just going to make myself small so you can see it. And it should be, it's now possible for you to do this, particularly if you've already completed the lab for this week. But your first step in success with this assignment is completing the week 10 lab. So make sure you give it a go as soon as you can and attend your lab this week. The template is available now in GitLab. There it is. It is available, good. As you might remember, I've been banging on about getting the little wires for your disco board for about 6 weeks now. So really, I expect that everyone has that problem completely sorted out. I am just waiting for the emails. I'm sure that there are people out there taking this class who have missed this big red attention box saying you need to get your little wires. And if that's you, you haven't got your little wires and you don't know how you're going to get them, then get in touch with me as soon as you can. And I can either encourage you that really you can get them, because often all it takes is heading out to JCar Electronics if you're in Canberra, or a similar kind of electronics shop wherever you are. But I can give you some encouragement. I've also got some right here, so if you're in Canberra and need to pick up some wires, it is possible to get them off me. Oops. Everyone now has way too many jumpers. Yeah, everyone. I mean, the previous versions of this course, we bought, about 2,000 little wires so that we'd have a couple to give out to everybody. And then in your labs in week 10, we would normally give you 3 or 4. And that's fine. Then every student would have 3 or 4 little wires. And now I'm getting you all to go buy them, which is fine. It only costs a few dollars. But then you end up with 10, 20, 30, or 40. So you have a lot of little jumper wires. That's okay, Adam and everybody else. I've got a lot of little jumper wires too. I've got a little jumper wire cupboard in the garage full of all of my electronics projects. Now, I think one other kind of general topic, and this is a little bit this is a little bit maybe left of field. This is not a topic about how to understand about computers. This is like how to be a student at the ANU, particularly now that we're online. Let's see what's saying here. Oops. I think Bianca is saying that she'd want to donate some wires. So far in the course, we've been looking at these topics where I think the best way to learn the topic is to watch my lectures. But over the next few weeks, starting last week, networks, operating systems, architectures, we're doing topics which are described in like 1,000 different computer architecture textbooks. There's literally this course is called Computer Organization and Program Execution. There's lots of textbooks with a title like Computer Organization. And what I found is that maybe it would be good for you to go and have a read of them. So, Computer Organization. If you just go into the library at ANU, and if you want to physically walk into the library when it's available, then that's great. But it's also completely possible for you to visit the library virtually, and you can look at some amazing textbooks that are really interesting just from your seat. So this is the one that I've been looking at a lot recently, Essentials of Computer Organization and Architecture by Lyndon Null. I don't think you need to buy it because it's available from the library. You can read the full text of this one right from the library. There's this other book called Computer Organization and Design, Hardware Software Interface. That's one we often use in this course. It's one of the recommended texts because it's got a very good description of how the ARM ISA works. I can see that there's one copy in the library and someone's borrowed it, so that's not so helpful. This one is great because it has the full text online. So I just don't know what happens if you click that. You know, you have to have logged in here, right? Probably not going to show you my password, but haha. Where is it going to take me? It takes me to learning.o'reilly.com. Well, that's interesting. O'Reilly is a publisher of computing textbooks. And I've got their site open here. And in fact, you can just log into O'Reilly, learning.o'reilly.com from with your ANU email address and password. And yeah, someone says I've got a very long password. Of course I've got a very long password. Who doesn't have a very long password? If your password's like 6 characters, you're totally doing it wrong. O'Reilly, you can read all O'Reilly books and watch all of their videos and look at all their other stuff for free. It's all like available to you as an ANU student, which is kind of amazing. It's an incredible resource. I've been reading this book recently. This is my bedtime reading just to recall a few things about how operating systems work. The Linux System Programming book from 2007. If you want to just really start to understand how Linux works, that's a great book to have a look at. I've got a few other things bookmarked in my my playlists. A few chapters from the computer organization book. I guess what I'm saying is that there's lots of, when you Google around online, you find a lot of websites. For these topics, Wikipedia is not too bad. It's got some great articles, but there's a lot of websites that are just trash, like things like Guide to Learning IT or something. And it's a website full of ads with really incoherent explanations of some of these topics. It's not even loading my playlists now, but there's a lot of good books. Well, where's my books? I wanted to show you some stuff. Well, I'll show it to you in the Essentials of Computer Organization and Architecture. This book has some, it doesn't help you that much with understanding how to do ARM assembly programming, but that's fine. If you want to recall about signed integer systems, this would be a great place to look. If you want to revise on how digital logic and Boolean algebra works, this is a great place to look. It goes into far more detail than we did in the lectures. If you want to look at memory, this will work as well. Basically, there's a lot of stuff that in this course we skip. In a typical computer architecture courses might go into greater detail. And a lot of a standard kind of computer architecture thing to do is to talk about how memory gets cached. So the CPU is requesting some memory, and on a big computer, there'll be some memory which is closer to the CPU. So it's actually built into the die and right there next to it, so it's faster to access, and that'll be the cache. So then there'll be some strategy that when you instruct the CPU to get some memory, the memory controller doesn't just get the memory you want, it gets a whole bunch at once from memory, puts it in the cache on the guess that in fact you want not just that bit of memory, but some bits that come right after it. And that will be really helpful because once the memory is in the cache, it's much faster to actually access it. I'm not sure how that works exactly on the disco board, but that's something which is often taught in something like COMP2300, but we don't go into detail in this particular course. So I'm not going to ask you detailed questions about caching in the exam, obviously, but it's interesting nonetheless. But most interesting here, I guess. Oh no, this is the wrong edition. Which edition is this? I do need to go to my playlists. It's frustrating. The latest edition of this book, the 5th edition, skips a chapter, and I don't know where it is. So I'm trying to find the 4th edition, which has the networks chapter. Here's my playlists. Okay. Sometimes to make these books shorter, they just take the last few chapters and put them online, which can be really frustrating. Oh, no, it's still the wrong chapter. Now it doesn't load. Come on. There's the 4th edition. Okay, chapter 12, network organization. And the point of chapter 12 that I wanted to show you, was that they have this little history of networks, and they have a really good explanation about the 7-layer open OSI model, the Open Systems Interconnect Protocol model. And they've got this kind of analogy about how this model would send you data in terms of like kind of food being prepared at some factory and then being sent to a customer. And so there's all of these kind of wrappings that go around it. First, the food goes in a box that you get so you can access it. That's like your application layer. And then the food gets packaged with a bunch of other boxes, and then it gets put on a truck, and then the truck goes out into a freeway, and the box goes into a distribution center. So there's kind of these analogies about how these layers go. And it's certainly, it's in some sense useful to go through a different way of explaining the OSI model, particularly if, as we went through last week, was a little bit fast for you. But I'd rather you went and read this book on your own. I've got a link to this in the networks lecture, which we'll see in a minute. And it's available to you on learning.o'reilly.com. So I say, your job as students is not just to listen to me, but to go and do a bit of reading about these topics. I've provided you with a link to the reading. And this is your way of making sure that you understand this stuff. So my little talk about how to use the library is over. So where were we in our networks lecture? Because we've got a few more slides to get through. So we did the open systems interconnection model, maybe called different things in different places. With these 7 layers: application, presentation, session, transport, network, data link, physical. Layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. Okay, and then we were talking about some standard protocols and how TCP/IP doesn't actually match up with OSI. As often happens, all of these people who were discussing OSI, they were sitting around tables discussing how great it was. We're going to invent this fantastic standard, and then meanwhile a whole bunch of hackers were just sorting things out, and the hacked up version ended up being the one that was everyone wanted to use. Hackers as in people who are building computers, not breaking them. Okay, here we are. So we're now going to talk for maybe about 20 minutes about a few examples of, or at least one other example of a kind of serial interface for connecting computers to peripherals. And I guess we talked a lot about that asynchronous serial protocol called MIDI, or just normal old serial, you could call it, on Friday. And we did a little demo on my desk. That was a lot of fun. And then there was this other concept of synchronous serial. So the difference between synchronous and asynchronous, if you remember, was that the asynchronous one would just have a ground wire and then another wire that's giving you this signal. This doesn't really make sense. This is just a drawing of the voltage going across the data wire. A signal that goes up and down, and both ends need to agree on how fast the bits are going to go across that signal. And so as soon as this one starts sending bits here, then the other end starts counting at 9600 bits per second or 31250 bits per second. And they just have to agree on that timing synchronization. So there's no linked clock between the two systems. And the other option was a synchronous serial connection where we actually have another data line, another line which will be the clock. And the clock is just going to go up and down. So whoever is initiating this connection can run their clock, and the other person now just knows about it. They can just follow along with this clock, and maybe every time they see an upswing, you read a byte off. So that's a 1. Every time you see a downswing, that means don't read a byte off. And the advantage of this one is the two sides don't need to understand about the clock. Or they both don't need to. Only really one of them needs to understand about how a clock works. And the other one can just be following along. And this means that means a couple of things, but it means that the side that doesn't really have a clock can be very simple. And it also means that you can go as slow or fast as you can, as you need to, and the clocking side can just change that speed and set it all up to suit itself. So the example we're going to talk about for synchronous serial is this one called SPI, Serial Peripheral Interface. And you've all used an SPI device, I'm sure, because every one of these things is an SPI interface. A really, really simple serial device. So this thing, this SD card with 1 terabyte, that's a big SD card. I never really noticed that before. Wow, 1 TB SD card. Anyway, distracting myself. This one is very, very simple, right? And you just want to have basically a tiny little circuit board with a buttload of flash on it, and very, very simple circuitry. And then whatever you plug it into, your phone, your computer, your camera, will have the smarts on it to be able to clock that line and send data in and out is very fast. The funny thing about SPI is it's not even a formal standard in the sense that it doesn't have an ISO number, but it's used by just gazillions of devices, and it has speed limited by, as the person who wrote these slides says, speed is only limited by what both sides can survive. Very simple electronics, and turns out to be a winner, as we all know, because we use them all the time. So how does this SPI connection work? Well, it's what we call a 4-wire serial protocol. So we often talk about serial connections, or sometimes talk about it as in the number of wires that are required, and we don't count ground. So we always need to have a ground connection. Let's just forget about that. But in SPI, there's 4 wires, and suppose we've got 2 devices here. This is going to be the master is like the camera. Apologies for the master-slave lingo. There's a concerted effort in computing right now to just think about the words that we use to describe things. And you know, it's a part of a larger movement towards ensuring that we have equity in computing and engineering, equity and inclusion. And it's not very inclusive to use language sometimes which people find inappropriate or references something which is painful. And there's various levels of this, and a very complicated issue for people, and depends on what someone's cultural background might be. But one instance is like trying to change the names of some things where it was kind of a juvenile joke by some hacker back in the day. Maybe it was funny in the 70s, but it's not funny anymore. And at some point, it might be better just to change the name of something. There's some people who just don't like the fact that we call some devices masters and some devices slaves. So it just is a painful reminder of the evils that slavery practices have had in the world, which is fair enough. I think if someone's designing a new API, then probably avoiding master-slave words is a good one, but it's a bit difficult to, we could call it like leader and follower or something, but then it'll be very confusing. You look at other SPI documents that are all listed in terms of master and slave. But I guess my encouragement is, if you're out there designing a new kind of network interface, choose language which is inclusive and equitable. Anyway, so we've got the kind of the camera or the computer is going to be the master in this setup, and the SD card is the slave. So it'll follow what the camera says. And the 4 wires, one's called MISO, master in, slave out. So that's a messages being sent from the SD card to the camera. Master out, slave in, messages going the other way. And then we've got a clock line. That's just going to be going up and down, clocking our reads and writes. And then we've got this chip select line, which is telling the SD card that it's the one we want to be talking to. We'll explain why that's necessary in a minute. There's a few details on this slide which you may not have seen before, but there's this thing called a shift register. The clock generator is probably self-explanatory. It's something which is going to make this signal. The shift register is just like the register on your disco board, it's a place where you can store a word of values. It may be less than 32 bits or maybe more. An 8-bit shift register is a really common electronic component. You can go and get one from JCAR. If you ask for it, one of the guys will have to go and turn around, or ladies there, and scrabble through a bunch of little drawers to find some little chip with some little legs in a dual inline package. And that'll be your shift register. Of course, inside a computer, the shift register is just probably integrated onto some other chip. So you don't actually see it as a separate component. But what it does is that it's just basically, maybe you can send a bunch of signals in here, your 8 bits. So I get 8, 1, 2, 3, 4, 5, 6, 7, 8. And then you'll have some kind of clock, and then it'll have an output. And then, so you load it up with your number, all of your 8 bits of your value in binary will go and be stored inside the shift register. They're safe there. And then you clock up and down on the clock line, and then the numbers will get shifted out one by one, and they sort of get pushed down through the flip-flops inside the chip. So you're taking something that's going from parallel into a serial format to get clocked out. So they're getting clocked out on the transmit shift register, and at the other side they're getting clocked in onto a receive shift register, and then the other side they're getting clocked in, and then at the other side, once they're done, the other side's CPU or whatever hardware can read that off and transfer it to memory or put it back somewhere where it needs to be. So that's what a shift register is. So this is our 4-wire SPI connection. The clock rate's flexible, so if you just make this faster, it'll all go faster. You make it slower, it'll go slower. You can just do it 1 clock at a time if you want to. It's full duplex, so they can talk to each other at the same time, both directions simultaneously. And now we can have a look at why we need that selection line. Oh, here's one more little thing. The selection line is going to indicate to the SD card when the computer wants to talk to it. So when the select line is high, that means I'm not talking to you. When it's low, it means I am talking to you. So in this example, the select line's gone low. Now the clock is starting up, down, up, down, up, down, up, down, up, down, up, down, up, down. And when the clock goes in an up direction, rising edge there, that means that both sides get to set the line. So the master is going to set the MOSI line and the slave is going to set the MISO line. And then when the clock has a downswing, that means that both sides can read from the line. So upswing, write, downswing, read. So that we're not trying to write and read at the same time. And you can see this interesting notation here. This is sort of typical for describing how a protocol with physical voltage lines would work. The clock has one defined way of going, but the voltage lines are either high or low, and they could be either. So this is depending on the data you're trying to send. So the diagram is indicating that there's a choice about which way they are. Okay, so that's the timing and data representation for SPI. It's a little bit simpler than the asynchronous, right? You have to have this extra wire to do the clock, but you don't have to have a start bit and stop bit because we know that as soon as this chip select one goes down, and as soon as the clock starts, that's time to read. So if we have the reason for this selection line is that we might have multiple SPI devices on the one bus. So in this instance, you can see the MISO line is connected to all three of these slave devices. And then we've got and the clock is sent to all three. And then we've got a selector in the master device, which is going to either select this one, or select this one, or select this one. So now we've got a little bit more of an interesting topology, right? On the MISO, MOSI, and clock lines, that's a bus. And then we're using the selector to indicate which person on the bus we're talking to. So the master is sitting here and each of those slave devices is connected to it. So that's a handy way to arrange things. It's pretty simple, right? You just have this selector with different places it can connect to. Here's a slightly different arrangement. You don't have to be talking both ways to these things. In this instance, we have multiple devices and we're talking to each one, only the master to slave, only talking to them, not listening. And we've still got our chip selects with the slave selector. And I guess the difference between this slide and the previous slide is that in this one, you really could only communicate with one slave device at a time, or one pair of devices can talk. Because if you had selected one slave device, it could be sending data to you at the same time as you're sending data to it. In this instance, you could actually select 2 or 3 of the slave devices simultaneously because the master device is not listening to anybody. Over here, where's my that's closed. So we're just sending information out. That means we can talk to multiple of them at once. So you could have some kind of, well, it's still a bus topology, isn't it? But It's only one-way simplex. What about this option? Somewhat different arrangement. Now we have the out from the master is going to the input of that one, then going to the output of this one, and that one goes to the output of this one, and then that one comes this way. So you can daisy chain a number of devices together, and then if we wanted to send a message which was directed towards one of them, we'd have to have some way of addressing it so that it could be picked up. So we could call this one OX00, and that one OX01, and that one OX20. And maybe we design in our messages that we're sending, just like in MIDI, had a channel indicator. We could say that in a message, the first byte has like the address is the first 2 bits, and then the last 6 bits are like message type or something. So, there's probably some standard protocols like MIDI which have different ways of doing this. But we can also invent our own if you're just programming your own devices and you have complete control over them. Adam has just suggested in the chat a good question, that if you were daisy chaining, then the slaves would have to have some extra smarts. And Gabe has asked how daisy chaining would impact transfer speed. I'm not going to make comments on electrical engineering topics that much. I think that daisy chaining in this instance would definitely slow down a transfer speed, because if you wanted something to go to, for instance, you wanted a message to get to slave 1, then it would have to be completely received by slave 3 and then passed along. Or maybe it could be offset by 1 bit at each time. I'm just trying to think through this logically from first principles. Because it could be that all of these are selected at once, and then master sends low, S1 receives low, and the very next clock maybe S1 sends low, and then S2 receives low. So you could only be like a few clock cycles delayed, and the speed might be the same, but it's just some latency before the message is received by the final member of the daisy chain. Bianca was asking what the benefit of daisy chaining would be. Well, the benefit in this case is that we don't have to have hardware indicating which of these devices we're talking to. So whereas in the previous cases, we had to have 3 outputs to go to each of these different devices, right? So you're going to have 3 wires. And if you're imagining you wanted to wire up a disco board with this, that means you've got to get the 3 little plugs and send them to each one. Okay, with the daisy chaining example, we don't have to have that. We're not using the chip select to make a circuit directly with each device we want to talk to. We're using some data inside the packets we're sending and making some address to send down the daisy chain, and then the device which responds to that address is like, oh, that's my message, I'm going to pick that one up. So we don't need to have special wires for each individual device on the network. And of course, when we have the 3 devices, that is not too bad to have 3 little extra wires on your disco board. But imagine if you had 10 devices. Well, suddenly you're going to run out of little plugs, And I don't want to break it to you, but even though there's a lot of little pins on your disco board, a lot of them are also already used for other stuff. So you can't always just use whichever one you want. I'm just going to move this over here while I address a few questions. Yeah. So Gabe has put this in terms of using fewer overlapping traces, which is great from a circuit design perspective. I mean, I'm just like a Arduino hacker with lots of little plugs. And the less little plugs that I have to plug into my Arduinos or disco boards, the easier things are. So having a daisy-chained protocol is a really, really handy thing. If you're interested in how these things might work in the real world, well, we certainly do use daisy-chained systems all the time with little microcontrollers. One that we often use is this one called I2C, which is actually only a 2-wire protocol. So that one, if you get like a microcontroller that you want to use, an Arduino or the little Wi-Fi boards by Espressif, and then you get some sensor like a temperature sensor or an accelerometer or something, they often will talk over SPI or I2C. And then your temperature sensor will have an address. So when you're coding this up, you'll have to write the address of your temperature sensor in your code when you send your serial messages on that line, so that the temperature sensor will pick it up and say, oh, that's for me. So that's definitely how these things work. I don't think you do need chip select for each individual device, Gabe. Just recall looking at that question. I think if you're daisy chaining, you just have a global chip select for that circuit. Here's some interface. If you want to learn about this stuff, it's all related to hardware, so you can find some great tutorials on sparkfun.com about them, which I refer to frequently when I'm playing around with this stuff. Yeah. Yeah, here's an SPI example where you need to use chip select, otherwise no one's going to listen. But in this case, we're just using one chip select line at the master, and the clock line connects to everybody, chip select connects to everybody. So once the chip select line is brought low, then the whole daisy chain starts exchanging data, and you'll have to pipe through this data all along the line of devices. And as they say, there's a lot of daisy chain stuff that people play with these days. One classic one is like addressable LED drivers. So if you've got a lot of RGB LEDs that you're building into some kind of crazy lighting installation, then you might end up using SPI to drive them. It's a very common protocol. Yeah, okay. Enough about networks. Let's see, we've only got a few slides left here, and I don't want to use the whole lecture on it, otherwise I'll run out of time. Another important network protocol, of course, Ethernet, little blue wires between all of our computers. This is something which has been under development for a long period of time, since the 70s. There's been different kinds of cables. We didn't always have the little blue wires. There was, first of all, people started with these really thick coaxial cables that had to be, they couldn't turn corners very well. You had to like have a connectors screwed into them to angle them. They had to have special terminators at the end, like the end of the cable couldn't just be left bare. You had to put a resistor on it and a little cap which would go over the end. And they were very inconvenient. I've only had very few experiences seeing old coax Ethernet cables, but typically like the little plugs you put in your house have these twisted pair cables. So they've got a lot of, not just a ground and a data line, but in fact 4 pairs of wires that are twisted up, and the twisted wire is good for doing differential signaling. So it's not just a ground and a voltage, but it's 2 voltages which are kind of moving away from each other. Anyway, we're not an electronics engineering course, so we're not going to talk about that too much, except for me to perhaps advertise another one of Ben Eater's videos where he takes an old Ethernet standard where they used to use what's called Manchester encoding to send messages over the wire. So this is the differential signal. We're at 0 in the middle, and one of them is going to up to +1 volt and then down to -1 volt. That's less than 0 to 5 volts. If you have to move a voltage less far, you can actually make it go faster because it takes time for the voltage to come up. So you can, a lot of faster protocols end up with less voltage changes. Now, the cool thing about Manchester encoding is that it's not like high and low. You're actually tracking the changes in a value. So if the voltage has a rising edge, then we call that a 1. A rising edge at the kind of time where we're clocking it in, that's a 1. That's a 1. And then up here, the voltage is kind of trying to stay at the top and then move down. So that's a 0. Then staying at the bottom and then moving up, that's a 1. And it's funny to see that once you get fast enough, voltages can never really stay still. It's kind of got to keep moving, and the thing that's the driver at each end, the electronics, has to sort of force that voltage to stay down, but still be in some kind of clocked rhythm. Anyway, I'm not an engineer, so I don't understand it, but it looks really cool. This video is great explaining how this works, and you can see him like literally pulling apart an Ethernet cable to get the oscilloscope in there and start reading off these values. Then of course, now we don't really use Ethernet cables. I like using them still. I have them in my house so I don't lose a connection between my computer and my router. But in many cases, Wi-Fi is now what everyone will be using for all of their wireless, all of their network connections. And again, there's many, many standards, even though it's the same the same radio frequency transmissions. Early standards came out in the late 90s. And then ever since then, it's kind of been improved and improved and improved. So that was called 802.11 was the name of the earliest standard for Wi-Fi. And then they keep adding letters like A, B, C, AC, N, G, with various details about how it should work. So the big picture here with networks is there are some things which are very relevant to your physical experiments with the disco board. That would be how serial connections work and how parallel connections work and what the little wires mean. And then there's stuff like this OSI model, which is very big concepts. But make sure you remember these basic concepts about topology, the direction of different signals, whether it's simplex or duplex or half duplex, circuit switching, packet switching, and how a protocol means that which bits of your data are getting stored in kind of the physical way that you're wiring up a network and within the bits of your packet itself, the bits of your messages. Yes, thanks Adam. We got a shout out from Adam for sticking to Ethernet wires. When I had to move to work from home, the first thing I did once I realized I was going to have to lecture from my desk was get someone in to install Cat6 in my house. So Cat6 wires so that I would have a reliable connection to my router, because I did not want to be, although I've got a great router, just the normal one I got from Telstra is really pretty advanced now, has amazing Wi-Fi capabilities. The more devices you have on your Wi-Fi, the more things are congested. the more problems you might have with getting a message through. And if I'm streaming and doing my job, I don't want to mess that up. Yeah, so remember these basic concepts. You'll come across this a lot, particularly in the third assignment, which is what I'm going to talk to you now about. So this is a little chat about P2300, a disco board sound control protocol. And this is highly relevant for you now because you have to implement it in your third assignment. But this is not a widely used protocol used in industry yet. I suppose we have discussed how MIDI is used in industry. There's a lot of problems with this protocol, but thankfully it's quite easy to implement, which is the reason we have you to do it as an assignment. Now, the protocol is going to have two lines, a two-wire protocol. And it's really a parallel protocol because you can't get away with just data being sent across one line. It's being sent across both lines simultaneously. Now, one line is dedicated to whether a sound should be happening or not, note on off. That's this one. And one line will be dedicated to what your pitch is. And you know, with MIDI, we were encoding a pitch as in a byte, encoding its number. But P2300 doesn't work that way. This pitch change is actually just flicking on and off, and it's moving through a known table of pitch values that should be played. So I'll show you an example in a minute, but here's what the architecture is going to be like. You've got your sender, disco board, right? It's got its little screen and its little joystick and a thing and a USB connection. And then you've got a receiver, which is another disco board. And you're going to connect. Oh, a weird sound happening there. I've got terrible blinds in this room and they never want to, they want to unroll themselves if they're not fully down. So one line is connecting one of these, disco boards together. And of course, in your assignment, you're not going to do it on two disco boards. You're just going to hook your disco board to itself, which will work as well. So here's an example of how this works. Your table of pitches, I've forgotten what it will be, but it will be something you have stored on your disco board in memory, and it will have the frequency of each pitch, right? 220, 240, 260. I'm just making it up, right? So when your pitch line changes, that means you're going to point some index through this array to get to a different pitch. And then when your note on-off line changes, that means you're going to get your synthesizer to play some sounds. So the pitch sequence index will start at 0 here, and then, so that means it's pointed to that pitch, 220. Then note on-off goes up, we play a sound, note goes off, we stop, goes on, play a sound, stop, go off. Then we want to play another note, different pitch. The pitch change line flicks on twice, one, then we move down to this one, not that one anymore. Where's my eraser? Again, move to the third one. So now our pitch sequence index is 2, we're at 260, and then wait for a while, then turn the note on off and play our sound. And so on. One more pitch line change here. On the rising edge there, it moves down to the last, to index 3, and play some more pitches. And note here that this one is on while that pitch is being changed and then goes down, and it hasn't made a difference because in P2300, only the rising edges of the pitch change line are recognized for anything. The falling edges are ignored. Not listening to that, not listening to that, and not listening to that. On the note on-off line, both the rising edge is important and the falling edge is also important as well. Yes, Mitchell has just made a very good point that these slides are, oops. On this slide, we've got some labels for the pins, which are wrong because we've changed those for various reasons over the years. But the Disco board P2300 protocol is the same. So that's what you have to do for part one of assignment 3 is to implement P2300. I'll just go back to the assignment for a little bit. You can see this person here has connected the pins correctly on their own Disco board. And of course, when you're doing assignment 3, you only have one Disco board, but you have to implement something that would work if there were 2 Disco boards. So you're going to have some code which is being a sender part and some code which is being a receiver part. And the receiver part should work even if the sender part is not sending any messages. Do you know what I mean? So sometimes we get an answer for part 1 where someone has sent some information over the lines, but the receiver part really doesn't work. The receiver part is also just reading numbers from a register that the sender part has set. And if this was on 2 different Disco boards, it wouldn't start. So you have to be very careful when you're designing your program for part 1 that you can have a separate sending and receiver part. Here's the pitch index table in the assignment, different pitches to play. And then your challenge for it is to play this song, right? We've got another little pitch duration table for you, but in this sense, in this instance, your table is going to be, you should be sending the information across the P2300 interface to the receiver part of your code, which then looks up the values in the table to create the sounds. And then you can listen to the sound of what it should sound like. It's not a very interesting song. It goes do 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 do, something like that, and then loops around. So of course you'll be using your experience with the sequencer to build this, but then extending it with what you now know about how to make connections, or what you will know about how to make connections on Disco boards in Lab 10. And I guess in some sense this assignment is known to be challenging, but that's because you have to have done all the labs to get there. So if you haven't done all of the labs, that's your first port of call. And I really hope that all of the students who are engaging with this course, and you're all doing such a great job engaging online with us, jump in and make sure you get those labs done, because if you don't have experience looking in the reference manual for the Disco board and you haven't tried out how to hook wires in and how to control interrupts and how to set timers, then you'll find that you don't know where to start with this assignment. This assignment is not hard if you've done all the labs and you've scaffolded all that knowledge, you've built up the foundations to get to the point where you integrate some sequencer code with some interrupt code and some networking code, but it is if you haven't done all those. Now in part 2, similarly to the other 2 assignments, same concept. In part 2, you have to do a more advanced network protocol. So your experience with part 1 will have, again, scaffolded some knowledge about how to hook up wires on a Disco board and control them. And then in part 2, you get to do something that you want to do, just as in the other assignments. So your options would be something like extending the P2300 protocol in a meaningful way. You could add more wires that do more stuff. You could implement a serial protocol, and in fact that's something which a lot of students choose to do. The great thing with doing a serial protocol is once you've set up the serial protocol to work and you're sending bytes over a serial protocol, then you can store whatever information you want in that byte. You can make messages that are 5 bytes long and have heaps of information that need to be sent. And you don't need to have little pitch tables. You can do something that's similar to MIDI or something even more advanced. It's really up to you. And so then you have a lot of scope for designing something really fun in your network protocol. And in fact, because doing a serial protocol is a popular option, we actually provide you with a bit more scaffolding to do that as well, and a little outline of how you might implement a simple synchronous serial protocol with just 3 lines, a data line, a clock line, and a control line. So similarly, the control line is just going to tell the receiver that a message is coming, just like in SPI. This is very similar to SPI, except it's only simplex. It's only sending data one way. And then you've got a clock line, and then the data line is going to either be low, 0, or high, or 1. And then there's some steps. We don't give you too much information, but we give you some steps about how you might have to do it, and a little example of some data sent across that line. Josephine is asking me, if the pitch line only recognizes the signal rise, how would you tell it to go down a pitch? That's a really difficult question. I wish I'd thought of that. Obviously the assignment's broken. It's not broken, no. How do I go down? It's, as Adam has said, it's in the FAQ. Let me find it. I'm able to increment through the sequence, but how can I send the decrement pitch index message? Oh boy, it can only tell it to increment, but not decrement. So the hint here is you're going to still play the sequence using the P2300 protocol. You just have to send more than one message to get into the required state. So I think if you look really carefully at how P2300 is defined up here, really, really carefully, then you will understand how that is intended to be done. Yeah, I think this paragraph about the P2300 pitch sequence will indicate to you what you need to do. And in fact, we made the sequence specifically having to decrement pitches so that you would have to solve this little problem. And it's not a hugely difficult problem, but you do have to make sure that your pitch sequence in table and your senders and receivers are working correctly to be able to decrement sequences. Yeah, and Mitchell has made a very important note. You're not allowed to change the table. The table is set. This table is set, and you're only allowed to access it in terms of the P2300 interface. We'll discuss more about this over the coming weeks. I think there'll be a lot of discussion on Piazza about it, so I encourage you to ask questions on Piazza. If you've asked a question which is sort of too much of a hint, we'll just change your post to private, so to have a discussion with you about it. So don't be afraid of asking questions. Any question is fine, and we will answer them. Yeah, Adam has said bad protocol. Yeah, terrible protocol, but interesting assignment question. You know, sometimes as part of our part of learning things, it's not only good to learn how to do things the correct way, but it's interesting to learn how to do them the wrong way, because you kind of learn more about how the world fits together in that way, right? So often I'll ask you an exam question like, okay, here's all you know about computers, let's do things differently and you can impress me with your knowledge. Now I've got a big problem, which is I've only talked about networks today. I haven't talked about operating systems at all. So I might start up my operating systems talk at this moment. And of course, we've got all Friday to talk about it too, so I'm not too stressed. But I do want to get into it a little bit today. Week 10, operating systems. Woo, new topic. Now, I guess operating systems is something which we have not talked about at all in this course, because so far you've been writing code directly on your disco board, and your disco board doesn't have an operating system. Well, what does that mean? That means that when your disco board turns on, it runs one program, and then when that program finishes, that's all it does. And an operating system is some kind of other program, like a higher level program, that is going to allow, a user of the computer to do different things. And I think intuitively, you probably have an idea of what an operating system is. But the point of the lectures this week is, I guess, to kind of break your assumptions a little bit about what an operating system is, so that you see that there's perhaps two different things that you might think of that could be an operating system. And one of what you think an operating system might be, I guess, is what many people think of an operating system, which is like all this stuff, right? All these little icons and these menus and a desktop wallpaper and ways of looking at different screens, right? So the operating system for a normal user perspective today in regular computing, desktop computing, is how am I going to access all the different programs that I want to access? How am I going to operate them at once? Put them on the screen in different ways. But I want to think, or challenge you to think about what an operating system is at a deeper level or under the covers. In fact, what is the core parts of an operating system which let it do all of this stuff? Let it run multiple programs. Let it have an interaction loop with a user. Let you write programs in a programming language which might work even on different operating systems, which is wild. Would work on different computers, different architectures. So we're both coming from the top of breaking down that knowledge that you have about operating systems, and also building up from the bottom from the disco board level, because in the lectures the week before last, we learned about how to do a context switch on a disco board. And that was the first time we were able to consider running more than one program. And it's something which you work on in labs next week and the week after, as sort of the final labs for this course. So the core question of this is, what is an OS? That's really the only question we talk about today. What is it that an operating system is doing which makes it interesting, which makes it special? So here's some operating systems. If we were live in the classroom, I might ask you which of these are ones you might recognize. And if you look around, you might see a few that you know. I know that there's a lot of people who are fans of this one, the Linux operating system. I'm also a fan of this one over here, the Mac OS, the Apple operating system. And there's many in the class who also love this one, Windows, the big guy, the leading operating system for many years for desktop users. There's another Windows, right? There's been multiple kinds of Windows over the years. Arch boy is the time. Leopold's an Arch fan. That is true. And then we've got some older ones. You might remember this one. Well, I remember it from when I was a kid. MS-DOS, the operating system which was Microsoft's command line operating system for personal computers for many years in the 80s and 90s. And at that time when I was growing up, the first computer I used only had DOS when I was really little. And then there were computers that had DOS with Windows. But Windows was a program which ran on top of DOS. So you still had to have DOS back there in the well, we're not going to have operating system fights in the chat. I'm just going to no OS flame wars. No OS flame wars in the chat, pools, lol. There's some ones here that you might not recognize. This one, BIOS, that was a really people loved that operating system. It was sort of a bit more academic for workstations in the 90s. Fell off the bandwagon. There was a few years when there was this disaster at Apple in the late 90s. Apple was like almost broke as a company, almost went bankrupt. And they somehow managed to get back online and become very powerful after that. One of the things they did was buy a new operating system. And they actually bought an operating system or a computing company called Next. And part of that was because Steve Jobs, the founder of Apple, worked at Next after he was kicked out of Apple. He started another company, and they bought Next and integrated the Next operating system into their system, which was then called Mac OS X, which is the ancestor of the operating system we use on Macs and on iPhones and iPads today. But the other option was that they were going to buy BEOS. And so they didn't buy BEOS, and BEOS kind of fell by the wayside. Another important one here is Unix. I think that's the Unix symbol. And the Unix you might have heard about, but probably have never used like exactly something that is called Unix, because there's lots of operating systems which are compatible with Unix or inspired by Unix. Mac OS is one of them. All of the Linuxes are Unix inspired, but Unix originally was a commercial product. So we'll talk a bit about that history as well. A very influential product. Yeah. And there's even things like browsers, Netscape, can be considered to be operating systems now as well. So what is it? I already said you have to break your assumption. It's not the user interface. The user interface is cool, and I love user interfaces, but your desktop environment, even your command line environment, that's not an operating system. That's not it. What it is something in your computer which allows you to run these many programs and have these programs play nice with each other and provide an environment for these programs to operate so that they're simpler to program. Some more amusing comments. I think we're getting to the end of the lecture, so the flame wars are starting in the chat, which is fun too. So one way of thinking about an operating system is a virtual machine. And that's something which is a bit of a difficult topic to explain. A lot of people, when I set aside exam questions, they'll write, well, an operating system is a virtual machine, full stop. And well, that doesn't get you very many marks, because you need to explain to me what that means and what it is that it has to provide for that. So a virtual machine, that means that the operating system is sort of providing a standardized kind of computer to the program. So the computer can talk to, rather than talking directly to the program, rather than talking directly to the computer's hardware, can talk to the operating system's version of the hardware, or its virtual version of the hardware. And then the operating system talks to the computer's hardware on its behalf. So when you're writing a disco board program, you're doing things like directly setting a register in a memory mapped register for controlling some hardware device, like an LED or a GPIO pins or the interrupt controller. And then if you wanted to write code for a different microcontroller, you'd have to learn all about how the interrupts and LEDs work on that controller. So if you wrote a program in ARM assembly, and then you wanted to run it on an Arduino, which is an Atmel chip, well, the assembly instructions are different, first of all. And second of all, the hardware locations in memory for all of the interrupt stuff are different. So your code for the disco board is not going to work on the Arduino. So instead of that, we want to have some system that lives in between so that your code could be compatible with both. And in fact, often, the compiled code, if you're writing in C and it was compiled into assembly, the C compiler might help you with some of these things, but it wouldn't help you with the special memory mapped register locations. That stuff is all kind of hard coded into your code. So the OS provides what we call hardware abstraction, so that when you're talking to your hardware on a machine, be it a disk or memory or peripherals or USB devices, you can talk through some standard interfaces, and then the operating system is going to speak to the computer on your behalf, and the operating system knows exactly how those interfaces work on your computer, and then your program could work in that operating system on any other type of computer. Some other stuff it would be doing is like memory management. And at the moment in your programs, you talk directly to memory. So when you're looking at OX20000, that's OX20000. On a computer with an operating system, you will still talk to a memory address, but actually it's not the memory address you think you're talking to. So your operating system is running what we call virtual memory, where it's provided a memory map to your program for it to talk to, and then it has a memory management controller which will translate between that and real memory. And the advantage of that is that one process can't write in another process's memory. So there'll be some memory management, stopping processes writing over each other's memory, stopping someone reading some memory which is supposed to be secret or protected from it, and making sure that every process is kind of behaving itself. Another thing that now I've talked about multiple programs, there'll have to be this idea of context switching. And in fact, at a high level, we call that process management. I've already talked about hardware abstraction, I'll underline that. So the operating system is responsible for how many processes can run simultaneously, what to do with them when they're not running, what to do with them if they're behaving badly. Should we let them behave badly and lock up the system, or should we cause them to crash, right? And you know when you're on your computer and it says Linux, Ubuntu, or Mac OS or Windows has experienced a problem and something.exe needs to close, then that OS has just saved you, right, from a bad program. The program has done the wrong thing, it has had an error, it has tried to do something which it can't, and rather than your computer just crashing and giving up, your operating system has been like, well, hey there, slow your roll process. I'm going to stop you from doing that. And I can see now that actually you can't recover. So you're just going to have to be quit. You're going to be terminated. And I'm just going to send the user a nice message to inform them of what has happened. So the OS has dealt with this rogue process in a kind way, the kindest way from your perspective. Something else that OSs do, which is really important, is inter-process communication. So although there's lots of programs that can be self-contained, they do one thing, you put your input in, you get your output out, you're happy. There's also processes or programs which need to talk to each other to work correctly, or programs that need multiple processes to work correctly, or multiple threads. So IPC, inter-process communication, are the methods by which an OS allows programs to send each other little messages as they're running in order to collaborate, work together, and to accomplish more complex tasks. And that's one of the things which is really kind of thought of as being a important factor of Unix operating system. The Unix operating system was that you would have a lot of little programs and then use inter-process communication to chain them all together to do complex tasks. That's sort of an old school advantage of Unix. Yes, the other option of bad process management, if your process management doesn't work, is that you end up with the blue screen of death on your Windows computer, which I'm sure everyone knows, blue screen of death. Like, when you get this, then the operating system cannot continue running. The program has behaved so poorly, and perhaps the operating system has also behaved poorly, that we can't continue. So we have to reboot. So this is what I mean by a virtual machine, right? We're doing memory management, giving virtual memory to the computer. We're not giving the program direct access to our hardware, we're giving it virtual hardware or a hardware abstraction to talk to. Your program might think it's the only thing running on the computer, but it's not. It might be put on ice for a while and then thawed out and restarted, and we'll have some scheduler to arrange that. And then we have some ways even for processes to talk to each other, even if they're getting put on ice and thawed out continually by some scheduler. Another thing that or another aspect of the OS's role is to manage resources for you. So your Disco board is very simple. It has one processor, it has a range of memory, but we're only going to run one program on it at a time. One program on it at a time. And even though it has a lot of devices on board, we are encouraged to use either directly accessing it through assembly. I guess that's discouraged. Normally you would use the C programming language and the hardware abstraction routines that are provided by the Disco board's manufacturer, ST. But on a big computer with an OS, the OS takes this role. So it provides you the hardware abstraction. And in fact, if there's lots of programs running that all want to access the same thing, then the OS will coordinate their access. So we're not just coordinating access to memory, which is a lot of what we talked about in our asynchronism lecture, but also access to processors, access to storage like your SSD, your hard drive, access to networks, access to other devices like timers, GPUs, DSPs, other peripherals. And there's sometimes when, most of the time we sort of assume that multiple programs can coordinate on their own the different hardware resources, and there's sometimes when they can't. Like, I think it's, at least on my Ubuntu system, it's not really possible for two programs to both use my webcam. So only one can use the webcam at a time, and then it doesn't like that if the other one tries to use it. I'm not sure if that's an OS thing with the way that video is implemented in Linux, or an issue with the webcam, but that's the resource management part is not working in that instance. So now we do a little bit of a history of OS, and then I'll probably call it a day. We'll come back to this on Friday. A little history of operating systems. So now we're starting back at the very beginning of how computers were. This is a photo from 1957 of a mainframe by IBM, an IBM 704 at NACA. That was what NASA was before NASA was NASA. And at this time, computers were very big, very, very expensive. They ran programs for scientific or military or business operations. And there were very few options for what program was going to be run at one time. Someone would have developed their program, which would be stored, as we see here, on punch cards. And then basically we would set everything up and run that one program. It would take its time, we would get an answer, and that was good. And if multiple people wanted to run a program, well, this person might be in charge of putting them in one by one, getting the output as a printout, and sending them to the person at their office. So you would have submitted your job to be run on the computer in advance, and then this person operating the punch card reader there would do it. This person's job, I don't know what their job is, but maybe they're setting up the computer to be ready for another program to run. You can see all of the point-to-point wiring in there, really complex kind of handmade stuff. Weird switches. That's sort of typical of big computers before the 80s, was that there'd be some panel where you can literally switch in like the value of a register. So that would be like the binary switches to put in a value of a register, and then you'd indicate which register you wanted that value to go into that's your UI. These computers didn't have operating systems because they only needed to run one program. What IBM and the other mainframe manufacturers started to do was to build system monitors that could kind of be running all the time, waiting for a program to be loaded, and then maybe coordinate moving from one program to the next program in a batch, or running them all at the same time, in sequence at the same time, running them all together, and making sure that the outputs and inputs go into the right devices. But they weren't operating systems. They didn't have any of these virtual machine features. Over time, mainframes became more expansive and interesting, And the computer programmers started to want to do what's called multi-programming. So you might want to have two programs running at once. And a good reason to do that initially was that maybe you have to get some data off a tape or something, right? Or out of punch cards, you have to go through the deck and find it. Or wait for a printer to finish printing something off. And these things would take a long time, seconds, right? And we're wasting our time, wasting cycles on the CPU. And of course, given that this computer is so expensive and we only have one of them for like the whole university or the whole institution, we will want to run another program while the first one is still going. So we can slot that program in and share it. So that was where we needed to have the idea of context switching from one program to another. So still, it wasn't really providing this abstraction. We're still running the program on the same hardware, directly on the hardware. But the operating system would start to have features to allow one program to be waiting while it's waiting for a printer to finish or something, and the other program slotted in to take advantage of the CPU. Eventually, we would have some more, with these big systems, even some interactive programming, so that someone could be at a teletype terminal, maybe it's something more like a typewriter than a computer screen, right? And they would be keying in some commands which would then be directly run on the mainframe. And that was a very privileged thing to be able to do, right? To be an interactive user of a big computer like this, capital C computer. That would be, you'd be a trusted individual to have interactive access. There may be multiple terminals that could then be sharing time on the system. And then people started to develop operating systems that would be able to slice out access to those individuals and kind of account for it. They were called time-sharing operating systems. And then those individuals could maybe, the amount of time they were allowed to use the computer would be limited centrally, and every time they're doing something on the interactive terminal, it would be kind of ticking away at their quota for the month, right? And we have kind of the derivatives of that idea still exists with supercomputers. For instance, at ANU, we have the GADI supercomputer as part of the National Computational Infrastructure. And if you're doing a job on GADI, you get an interactive terminal. It doesn't cost you any quota to use the interactive session. But if you send a job to GADI to be scheduled and sent across, a zillion CPUs, that will count against your quota for the month. So you have to apply to have some quota. And if you want a lot of quota, there's a competitive process to apply for that resource. Now, in the 70s, the operating system started to get a little bit more interesting, and the computers started to get a little bit smaller, even though this doesn't look much smaller, right? This is a mini computer called the PDP-11, which was a really popular small computer. They didn't even call it a computer because they didn't want to compete with IBM's capital C computers, right? At that era, this was a computer, and this was like, what is it? People don't know what it is. So they called it a programmable data processor. It's a computer. Again, it's got the little switches for entering a register of information directly. Some computer scientists in the late 60s, early 70s started to have this idea that maybe we could have a programming language that we could use to write a operating system. And before that, all the operating systems or system monitors had been written in assembly. And these people were starting to have their crazy ideas about how operating systems should work. Maybe we can have multiple users using it more or less simultaneously and kind of interlacing all of their activities. And they came up with a way to have a kind of low high-level language. We already had high-level languages like Fortran and COBOL, which would be compiled into assembly. But they had a low high-level language called C, which would let us program an operating system, and then the C compiler would compile that for different systems. And before that, like, operating systems didn't run on different kinds of computers. If you had an IBM 704, it ran the system which was for the IBM 704. And if you had an IBM 650, that ran the system for that. and they had different instruction sets. And so maybe if you wanted to run the operating system on a different computer, there'd be some emulation mode where it could pretend to be this other type of computer. But now they were saying different operating systems can, or one operating system can be distributed to different kinds of computers. And the fact that these mini computers were a lot cheaper than the mainframes meant that a lot of computer science departments and scientists had them around as part of their research group's resources. And people started to get experimental and send data to each other and send operating system ideas. And this whole world of experimentation for how operating systems could work was opened up. And we still haven't seen an operating computer that really looks like one you would use, but we're about to. So there was an idea in the early 70s that some of these multitasking operating systems could work by one user. And there was a famous demonstration called the Mother of All Demos, where Douglas Engelbart's using a mouse on a computer, right, and doing this visual demonstration of doing some graphical drawings on a screen in the late 60s, which was sort of mind-blowing to people. And Xerox was taking these ideas and intending to create some kind of computer that people could use. Of course, it's still massive, more like a mini computer than a desktop computer we have. But it was running something like what we would think of as an operating system in terms of its sophistication, in terms of multitasking and being a virtual machine and resource management. And you can see it has a nice little mouse there. Xerox Alto was never really a big product. It would have been super expensive if it was. Not a thing that a normal person could have. But of course, Steve Jobs kind of ripped off the idea to have the original Apple Mac. The genius of that was taking all the good bits of this, which was the user interface, and doing it in a much simpler way on a very much cheaper computer. And then we have computers that you might recognize as ones that normal people would have. And this was in the late 70s, you started to be able to buy a computer, and there was people got interested in having one or using them as an individual. And you didn't buy something like a mini computer or a Xerox Alto, you would get a personal computer or a microcomputer, as they called them at that time. So these are a couple of the ones that were available at the time. That's the Commodore PET, Apple II, and the TRS-80 computer. Now these computers had an OS in some sense, but it wasn't a multitasking OS. It wasn't a time-sharing OS. It didn't have resource management. It was really just another kind of monitor which would give you something to do to start your program. So you can type in on the computer what program you want to run, and it would run it. And it's not running in the background then. It just points the CPU to that program and lets the CPU start. So they were very, very basic in terms of what an OS was. And that kind of set OS progress back in terms of what consumers could do, because these big computers, real computers, many people would say, had interesting operating systems and interesting programming possibilities. These very simple ones at home didn't. In that period, there were lots of other ideas about operating systems for computers on workstations. I talked a little bit about Next earlier in this lecture. And Next's idea was to sell workstations to scientific users. So they would have been very expensive, or they were very expensive when they were sold. And they had an operating system like this one, which was based on the Unix idea. I'm going to talk a bit more about Unix on Friday, but the Unix idea was that, Unix was this kind of standard way of setting up an operating system that these people had invented for PDP-11 mini computers using the C programming language to develop it. And then lots of other operating systems popped up which sort of went with that way of doing things, the Unix specification. Next being one of them. And this wasn't a home computer, this was a workstation for businesses or scientific users. And that was, even though it looks a lot like a Windows computer of the time, it would have been much more advanced in terms of the features of its operating system. And eventually there was the home operating systems kind of caught up, but they didn't catch up really until the late 90s, when there was a switch from like old Mac OS, the classic Mac OS, which was single tasking. It didn't have memory management. Each process was like directly using memory on the computer and could use it all. As a user, you had to tell the program to not use too much memory so that you could run multiple at the same time. And even then it would be kind of completely switching between them and not automatically scheduling the interaction between processes. At that time, there was sort of two versions of Windows. There was the Windows 95, 98, which was much more basic, and then Windows NT, which was a kind of inheritor to some of the more business-focused real OS protocols. And eventually, like, Windows NT turned into, well, that stream of OSs turned into what we use in Windows today, and the old Windows, which, like, where you could actually quit Windows and end up in DOS, disappeared off the radar in the late 90s. Yeah, so I've got some more written out information of this, but I just wanted to perhaps pique your interest by telling you about it in pictures to start with. But I guess it's kind of funny that there was this decades long increase in the capabilities of operating systems to provide all these features to programmers in the business computer world, mainframes. And then when we had microcomputers, fantastic, people can have a computer at home, but they're back to square one because the computers were so low powered, so low capability, that they couldn't run an operating system. They could only run one program at a time, and it was many years before that consumer level computers came up to the same level in terms of having kind of production ready operating systems. Yeah, well, I think I'm going to leave it for the day because we're at 10:43 now, so a few minutes over the end of the lecture. I hope that was that little history lesson about operating systems was interesting. On Friday, we're going to talk a lot more about how an operating system might be structured, and more details about Unix in particular, and what the OS would be doing or some details about how operating systems might schedule different processes and what it means to be a process at all. I've put in a link in the further reading of this lecture, a link to chapter 8 of the Linda Null's book, which is about operating systems. And that would be one that if you read it before the Friday's lecture, then everything will kind of make sense. You can read it after as well, but I suppose it's often useful to have a couple of different approaches to this knowledge. So I might call it a day and catch up with you later. Feel free to keep asking questions in the chat and we'll address them. Otherwise, catch you on Piazza and catch you on Friday afternoon.